Thanks the organizers for the invitation. This has been a collaboration with Ulysses and this group throughout the last couple of years. I guess we were part of this pilot project on TUMIT's scientific machine learning on doing reservoir simulation. Right? So I'll focus a little bit more on what we have done after the first year, but I'll touch base on what we accomplished in the last year or so. Okay, so again, the joint work with my student Daniel Badawi. He should be, I don't know if he's in the Zoom, and Ulysses group, and my former students Emilio and Marcelo and Georgie, and Ming as well, right there. Yeah, right there. Okay. All right. So what the problems are we looking at? So we're looking at problems on the reservoir simulation nature. So what is reservoir simulation? We want to simulate what is on the subsurface. Okay, and what is on the subsurface? We look at problems for hydrocarbon production. Right? Hydrocarbon production, basically, it is if you have a geological, place on the subsurface, we want to explore the subsurface. We want to get oil and gas out of that. But as well, with the latest trends in the clean energy, we want to store stuff into the subsurface as well. And one of the things that we want to store, it's called CCUS. It's carbon capture, utilization, storage. That you inject the CO2 on the subsurface, and you hope for them to be stored in a safe place and last for a long, long time. Okay, so that's the kind of simulation that we're looking at on the subsurface, right? So use CCUS, but as well, actually, I need to run today to another place for submitting a proposal for a what's called blue hydrogen. So what is that? It is you are we can use hydrogen for fuel as well, but we can store hydrogen on the subsurface as a way to recover energy, clean energy. Okay, and the difference between CCUS and blue hydrogen is that in the CCUS you want to store the carbon CO2 in the subsurface and not touch this anymore. But on the blue hydrogen, which is a little bit more difficult problem, it is you want to store in the subsurface, but you want to recover at some point, right? So that's and to do that we need lots of simulation, which takes a long time to do it. Okay, so those are large scale systems. It's computationally expensive. If you look at the time that it takes to do one simulation, it is several hours to days. If you have a very complicated reservoir, but today we are looking at uncertain quantification that we need to look at multiple of those simulations, multiple hundreds of those simulations, so you can do the math how long it takes. Okay, so usually you're interested in optimizing the quantity of interest. Certain quantification constraints, and that's our bottlenecks. So what we're looking at, we did a fast and robust ways to obtain optimized answer. So my interest on scientific machine learning, it is actually on what we call model reduction, which is try to determine something that can replace eventually a simulator job. Okay. All right. So what tools do we use? As I mentioned, we use reservoir simulations that can do, that's a classical PDE here, discretization. The problem here is that this equation, I'm not going to talk too much about this equation by itself, but this is a two-phase flow equation in porous media, which is a classical parabolic hyperbolic PDE. So that has some issues, and that's one of the things that we developed with the group of Ulysses. I'm trying to solve some of these problems with the hyperbolic partial differential equation. Okay. But what I'm going to talk about today is something that got down to us with my student Daniel, that is a little bit more simplistic than just doing reservoir simulation. Okay. So what I'm going to talk about to you today, it is what we call a well-tested. Okay. The problem with the reservoir simulation is that we need to know all these properties that goes into this equation. And nobody knows those properties. Okay, why? Because you have only drilled a few wells on the subsurface, and you're trying to infer kilometers and kilometers, miles and miles of geological media, which is very, very hard problem. Okay, so what a reservoir engineer does is something much more simplistic. What he does, it is what's called well testing. So well testing is as follows. Let's assume that you have a couple of wells and you're shutting, some of these wells. Okay, so you are producing for a while. So if you look at the production here in the bottom, you're producing for a while, and all of a sudden you're shutting the well, which means that you close the wells for some time. Okay, so one can look at a pressure response if you have pressure gauges at some of those other wells that you have closed, right? These are injectors, and you're producing out of these wells. Okay, so if you look at the pressure response of this, there is a signature for that, and this is given by the partial differential equation, first order partial differential equation, and so forth. Okay, so what the reservoir engineer does, look at this signature and try to infer what are the properties of the reservoir. Okay. And in a very simplistic case, there are analytical solutions to do that. And when you consider homogeneous reservoir, radial flow, and so forth, okay, which is never the case. Okay. So what we are trying to do then, it is trying to mimic this idea of well testing, with a machine learning approach. Why? Because it, although it is fast, it requires you to shutting the well, loss of production, even delay of the production, and can cause serious problems if you're shutting the well and the well doesn't come alive again, right? But there's only analytical solutions, simple solutions for simplistic reservoirs. Okay? So that's the problem that we're tackling today. And so what we know, the only thing that we know from that equation, it is the physics. Suppose that we have no data, right? We only have pressure, maybe pressure solutions, but we have no properties whatsoever of this reservoir. Okay. So what we can do, we can look at what we know, the physics that govern that relationship. Okay. What are the physics? As I pointed out to you, the PDE. Okay. So what we're going to do is try to implement a scientific machine learning to that type of solution. So here you go. So just a couple of examples, not going to dwell too much on that, but here is a slightly compressible flow, single phase flow. You see that's a linear equation on the top. But what we've done here just to get it started, it is as follows. Suppose I have only two wells, one injector and one producer, and I look at the solution of the flow at 500 meters out of this well. Okay. If I look at the PDE and throw this to a machine learning or scientific machine learning approach that I create loss functions here with no data, only look at the PDE, I get a solution. And by the way, so here's a little bit more details, a couple of loss functions here that we determine for initial conditions, for the pressure distribution all over the place, and for the initial condition. If you go there, simplistic problem, you get really a perfect match. Okay, so here's a solution on the left-hand side with no data whatsoever. You're matching the pressure at particular days. Okay, and if you compose this pressure match in days to well flow, you create a well flow system. So you can actually determine even the well flow into the well. Okay. No properties. I don't know properties yet. Okay, so then you can keep going and do a little bit more about the radial flow, and that's what get us stuck at the moment. Why? Because if you start to do something more complicated, and it's not complicated at all, I mean, there's some analytical solutions to do that. What the problem is with the radial flow, you have a if you implement what we've done in the previous slide, pairs things, and the reason is there's a steep gradient of this pressure around the well. Steep gradient around the well. Okay? So the way that we solved that problem then was as follows. So here's the solution with a solvable way. And the way that we've done that, it is we use what's called domain decomposition. We create a series of domains, if you will, right? And each domain, we had a pin, and the pin itself, we imposed not only loss functions with pressures and initial conditions, but fluxes that can match all these domains as well, on the boundary of the domains. Okay? And that's how we got this, this solution right here. Okay, again, really well matched. Okay. Now, just 1 minute, I know. What happens if you don't have properties? If you don't have properties, then you have a varying solution on the noisy data as well. And one can handle that by incorporating data and as well determine the parameters that we don't know. Here's the solution with a determining the prediction of the, let's say, the permeability in this case. And you see that the true permeability is 120 million RC, and we're getting closer and closer. If you allow time to go, epochs, we're getting closer and closer. So the beauty of this, we don't have to shut in any well. We don't even have to run tests on the field. We get the equation and we know exactly the property of the reservoir. Okay, and we can do this for many things here. If you don't know the pressure itself, actually the length of the distance between wells, you can actually infer the distance between wells as well, and you can even get initial conditions of the reservoir as well. Okay, just to finalize, that's some problem that we try to solve now, because we came up with another problem that we solve as well on this paper with the Ulysses group, which was if you go to two-phase flow, things become a little bit more difficult given the nature of the PDE and what's called butter leverage, and there's shock waves and so forth that one needs to solve as well. Okay, so we can read the paper. And just a final comment here, what we are moving to. We are moving to develop what's called two type of frameworks for doing this reservoir simulation. One is to ETCO. There's a couple of papers here on ETCO, and the other one is the PN11 that we can handle much larger problems, much more complicated problems, and so forth. So hopefully, keep going forward in the next few years. We're gonna come up with these two systems that you can just give the data or even minimum data, and you get a solution to your reservoir simulator. Okay, thank you so much.
We have time for one question.
About the data, how you collect the data? What kind of data you have in your metrics on the first slide?
Here,
no, previous one. One. Oh, next one. Next. No, I mean back.
okay, so
What kind of data you collect and where you get this data?
So here, I mean, in this particular case, there's no data. So it's just a PDE. So you assume that you have a domain, you have collocation points on the boundary, and on initial time, initial condition, and on the domain. This is randomly sampled. Okay? If you have data now, this is just only with no data, let's say external data. Okay, if you have data like this one, you're collecting pressure rate. Okay, so you assume that one of the wells, you can measure the rate, or you can measure the pressure. That's usually the case. This is the most common way of doing that. You have some data which come from the shutting the well and get readout from pressure gauges and the flow meters.
And related with the subdomains, the subdomains are connected each other with the models of the.
Yeah, so this is one. So how this came up? This came up on the fact that the problem here is that the size of the well, it's much smaller than the size of the reservoir. So that's why you have these steep grades. So what Daniel started to do was say, well, let's assume that I have a really big well, right, and the relative size of the reservoir. I'm start shrinking this well. Okay, so that's why he came up with he saw a problem with that, right? And what he has done was to divide this up into a logarithmic fashion. Okay, so this pressure, if you look at the equation, pressure actually moves logarithmic. If you look at the analytical solution of that equation, it's logarithmic, right? So this is kind of this is just a depiction, right? But it's kind of a logarithmic fashion. But right now, it is just a user-defined. The number of layers and how you're going to distribute those domains, user-defined. And that's we want to try to do something more automatic on that.
Okay, that's great. Thanks a lot.